There's two ways to convert cellulose into fuel. One is to use enzymes derived from bacteria or fungi and convert the cellulose to sugars and therefore go from sugar to alcohol, rather like the sugarcane route. So you're using cellulases to break down the cellulose. There are problems with this methodology, and I won't go into them in detail, but the yeasts used in the second part of the process are destroyed by the remnants of material from the first part of the process, and this in itself is becoming very problematic. Novel microorganisms need to be engineered, and that's where a good deal of excellent research is taking place, and that's not what I'm addressing myself to. We're in competition, frankly, with the people who are developing that route. So the alternative is a catalytic route. This is taking carbon dioxide and water vapor from the atmosphere, using sunlight to convert it to crops, and then taking this biomass and extracting from the biomass the food product, and from the rest of the biomass extracting fuel. And that's the route that I want to discuss. Now let me just say a word or two about methodology. What we're doing, and this is the work based in Cambridge, is pulling together a large number of different modern techniques, including a range of experimental techniques shown here: infrared spectroscopy, supersonic molecular beams, structural techniques, diffraction, and real space scanning tunneling microscopy, heats of absorption measurements, femtosecond pulse laser spectroscopy. So all of these are used in conjunction with theoretical methods, density functional theory, and kinetic modeling, so that we can begin to work from laboratory to the practical use of catalysts. Now, this is a detailed mechanism. It rather parallels what's happening in molecular biology. We're saying, let's pin down the atoms and atomic behavior, and then we can design better catalysts for the future. And there are now some very good groups, not least here in Aarhus, working on this kind of base. The experimental side is wonderfully demanding, and I have to show this slide because this is our single crystal calorimeter that enables us to measure bond energies experimentally, a crucial part of understanding the process, but it's also a crucial part of benchmarking how well the quantum theory is doing. So always energetics is the big test, energetics and crystallography. But I show this because the thin films that are crucial for the measurements we make are made here in Aarhus by one of those wonderful Danish super technicians, Jacques Chevalier. Oh, he's French, but he works in Denmark. So that's one technique, enabling us pulse by pulse to measure the heat released and therefore bond energy variation with coverage under well-defined conditions. Just to mention, our newest technique is a new diffraction technique which uses very small currents. 1 nanoamp is all we use for a second or so to get full structural information from a surface, and enables us to move to looking at systems which are electron beam damaged, and many of these are the systems of interest in catalysis. And then density functional theory. So using density functional theory, many systems can be examined and used or discarded for tests in catalyst beds. And this is the technique that I consider to be very powerful. It has to be benchmarked against experiment, and in our laboratory we have both the density functional theory and the experiment going on. Now let me, having introduced you to where surface science now is, come back to the work that we're doing. We're expressing this here in the form of a carbon cycle. So we're saying we're starting at the top with carbon dioxide and water, using photosynthesis to create biomass. Now, remember, from the biomass, we're taking the food off. So the first product is the food product from that process, which is the sugar and starch part of the plant.